Hello, welcome back. For this video, we're going to be reversing the player class a bit more because all we have so far is the health, and we're also going to find an entity list. For this, we'll be using three things. We'll be using Cheat Engine, of course, reclass, and the entity list finder, which I'll introduce to you if you're not familiar with it. And of course, I'll show you how to install it and set it up as well. But by the way, if you just found this video randomly, this is part 3 of a L4D2 external series. So I recommend watching that first before this one. Anyways, let me show you how to install it. But before that, just a heads up, this tool isn't a magic fix for finding entity lists, and I hope you don't treat it like that either. It's more like an alternative way to digging through the assembly manually. The biggest downside is that when you use it, it often throws too many false positives when it gives you entity list. Honestly, about 90% of the time, you get way too many results to manually check, and you would just have to resort back to using Cheat Engine and assembly. But if you get lucky, it saves a lot of time. Either way, if you don't understand how assembly is used to handle entity lists in memory, then you're not going to get any good results from this tool. But anyways, let's get this set up, and later on when we actually use it, I'll walk you through the results and explain things in more detail. So you're going to go to this GitHub right here, and you're going to either clone it or download it from the zip file. It's called the GH, Guided Hacking Entity List Finder. So go here, download it with the zip, or clone it. Then you're going to get to this file, and we're going to open the solution and build it ourselves because it doesn't come with a release in the Git. I'm going to click Build, Batch Build. Now, because this tool is an external tool, it doesn't use a DLL, we can go ahead and use the x64 version for x86 games, and it wouldn't matter. So if you have the option to use the x64 version, go ahead and use that. If your computer is 32-bit, then use the x86 version. But mine is x64, so I'm going to build that one. Once it's built, we're going to go back to the folder or the file. Once it's built, we're going to go back to the folder. We're going to go to Builds, x64, Release, and there's your tool. And we'll use it later. So basically, when you're trying to find the entity list, you want the most controlled environment you can get. So basically, the fewer variables messing with your results, the better. So if you were in FPS, you go into a bot match where you can control the bot's behavior. In MMO, you hit up a small dungeon or training room with as few enemies as possible. For an RTS, you stick to a 1v1. But the point is to just keep the environment small and as controlled as you can, so it's easier to narrow down the results and spot the entities, especially when you're using the entity list finder. For L4D2, I'm going to disable the bots and spawn in the zombies myself. Otherwise, we have to deal with bots running around and zombies constantly spawning, which would just be a massive pain. And I think we're also going to find a couple more offsets for the entity class, like position, view angles, velocity, and whatever else we might need later. Alright, so the first thing I'm going to do is disable these bots, so if I remember correctly is the status. And then we just kick ID and kick everyone else but me. That way the bots don't kill the zombies we're trying to find the address for. Then what I'm going to do is I'm going to stop entities from moving completely. So I think I need to enable cheats first, and then I can do that. That will stop the zombies from spawning or attacking me while I'm trying to figure out my player. So we're going to go back to reclass and try to find some offsets that might help us later for the ESP or the aimbot. So ideally, we want to find the position, the view angles, the velocity for predicting where we're shooting, and some sort of flag to tell us if we're dead or if we're crouching or something to that effect. So let's try to look for the position first, because that's probably the easiest one. And it's probably this, which are just, there's two copies of the same position. One is probably the head. Doesn't seem like it because they're exactly the same. Usually games have one position for the feet, one position for the head, but it's not in this case. So we're going to make this a vector 3. There we go. And let me change this a bit and see if we move. It's probably not going to move us because I just started a server by doing spcheats1. But it's still a valid position that we can use for calculating aimbot angles and ESP boxes for the enemies. And because I added vector 3s here, it's going to move every offset below it. It's a really annoying bug with reclass. And so I need to move this back to EC down here. Let me put this side by side and see if we see anything moving while we move the camera. So right after our health, right here you can see that when we start doing different actions, like if we crouch, it's 131. If we're standing, it's 129. Jumping is 130. And that's probably the state of our player. So let's call that flags. We can try to decipher what this is for later, but for now, let's just call it flags. Then we have another 62 here. I'm not sure what that is. Let's turn it into a vector 3, and let me change this to 20. Doesn't do anything, 20. And then we have another group here that seems to change together only when we're moving, so I'm guessing this is the velocity. So I can go ahead and name this velocity. This is another group above, but I'm not sure what it is. I'm not able to change it because I'm in a server, but for now we can just have it grouped. And yeah, this is not going to work either. And I think that should be enough for now. We can use that. We can use what we have so far to decipher the zombies' health and position, which should be a bit easier. This is all assuming the zombies and us share the same base class that have these parameters. So what I'm going to do is I'm going to spawn a zombie, Z spawn, or a tank. So I think those are the tankiest ones that could take us a couple bullets. I think normal zombies only take 2, and that would be a bit harder to find their health without them dying. And we're going to try to find his base address in relation to his health. Here we're going to take a big assumption and assume that the player and the zombie both inherit from the same base class, so they should have their health at EC as well. And from looking at the wiki, I know that the tank starts at 4,000 health, so I can scan for 4,000, shoot him, decrease value, shoot him again, decrease value, and we should have his health in one of these. And we're going to try to find his base address. And there we go. We have the same offset as our health and our player, so that confirms our assumption that they both inherit from the same base class, which is really nice. And it was ESI here. So this is the pointer to the zombie. We're going to add him. I'm going to name him Tank 1. We want to find at least 3, maybe 3 different entities, and then we can put that into the entity list finder, and I'll explain how to use it. All right, so now that I found the 3 tanks, we're going to attach to L4D2. Let me paste those real quick. There we go. Now the only address or the only field we can really control here is the max bytes between addresses. So basically, maximum distance between address is the maximum spacing allowed between consecutive entity addresses in that list itself. When it scans for potential entities, it looks for addresses that are grouped close together within this limit. The distance between these two addresses is more than the max bytes, then it discards it. So let me try to explain that a better way. So imagine, let me find a group of 3. This is our entity list. This is tank 1, tank 2, and tank 3. The distance between all of these is 4, because the size of a pointer is 4 bytes. So this would be a valid list. Now imagine this is tank 1, tank 2, and tank 3. The gap here is 4 bytes or 8 bytes, so this would not be a valid list. The order itself doesn't matter, so this could be tank 2, tank 3, and tank 1. It only really checks for the distance between any address here and their distance. It doesn't have to match the order exactly. Now this does make a big assumption, because imagine I scan for this tank, and then in that time, 5 different entities spawned that we didn't really account for. I scanned for this one, and a bunch of other entities spawned as well. And that would make it so, were it to find a valid entity list for this, it would be 20 bytes between addresses, at least, if it was a perfect list. So that's why we're going to get a lot of false positives when we start scanning. So let's start with 4, assuming they're all in order, which would be the dream case, which I doubt. Let's try 8. And we have 2 candidates, which is really nice. So we're going to go ahead and take this address. Let's make a new class, and we're going to go ahead and paste that in. It's going to make it a lot easier to see. Okay, so it does look like a list. And we're going to see where our pointers are. So we have CO, this is our first pointer, DO, and then we have 230 right here. So these 3. The max distance between any of these is 8 bytes, which is why this worked. Now, so we know this is valid. We hover all of them. This is a zombie. This is a zombie. This is a zombie. This is a zombie. Okay, these are all zombies. So this is entity list, at least for zombies. Not sure if it has items. We want to find the beginning of this list, because right now we might be right smack in the middle. What we want to do is we want to count backwards. So let's subtract 8 from this, which would be 414. We want to keep going back until we see what seems to be the beginning of the list itself, or at least an empty gap, which would indicate that there's no more list above it. Subtract another 4. Whoops, that should be a 10. We're still not at the beginning. Okay, my hex isn't that good. Let me open the calculator. Paste that address in. Let's subtract 24 bytes. Let's use that. And here we go. We're at the beginning of the list. We hover over it. It's a player, which is probably me. And this is a bunch of zombies. So this is the beginning of the list. We can go ahead and use that. Let's also close this. Let's go to cheat engine. Go to address. Add that. Delete all these 3. And let's pointer scan for this address. See if we get lucky. Just to the max level of 2. Anything above that will just take too long, and it's usually not reliable. So I always do either 2 or 3. And it said okay. I wonder if somewhere in here there's a way to tell the size of the list, but it doesn't seem like so. We can find that some other way. We wait for this to finish. And as you might have noticed, the entity list stores the base address of the class. So make sure you're using the base address of the class when you're using this tool and not just the position or the health. Because a list won't store the health of all players. It's just going to store all the players and then access their health from that list. All right, so it's finished scanning and we have a lot of candidates here. But I am assuming it's going to be in the server DLO because I am hosting a server, even though it's a single player game. It's weird. And it's the only one I think that has an offset of 0. So let's do, this one starts at C8. This one starts at D8. That's weird. Why would they both point to the same thing? Let me do the second one and hope for the best in both. We're going to take this and we're going to use this in our code as well. All right, so now let's go to offset handler, make a new offset here. Okay, offset entities and paste that in. Oh, I do want to change a couple things here before we start. Instead of using pointers directly, like I have been, I'm going to start to use unique pointers instead. We're using C++, so we might as well act like it. So unique pointer to entity, and we need to include memory for that. And instead of returning a pointer here, we're just going to return by reference. Here, we're just going to do std make unique. We don't have to delete the player anymore. And we don't have to change this to a reference. And you can return that you reference player. Now, if you're not familiar with unique pointers or shared pointers or automatic pointers, smart pointers, whatever you want to call them, basically make it so we don't have to delete memory manually like we have been. So unique pointers only have one owner. When that owner gets deallocated, the pointer itself will also be deleted. Shared pointers have a counting system. So if we have a player here in this class, and somewhere in our main CPP, we also access the player pointer will not get deleted, even if we delete the offset handler, as long as main CPP also has a copy of that pointer. For the entity, or for the local player, we want it to be a unique pointer. You only want the offset handler to manage the memory. For some others, like the entity list, might be better to use shared pointers since main CPP or some other files might also want ownership of that pointer. And since we have that, we can also do that for the memory handler itself. So let me do that real quick. And let me organize this a bit better because we're going to start adding a lot of things to this. And we also, we commented that, so we're fine. Make unique and the memory handler. Perfect. For storing the entity list, I'm going to be using the std vector of shared pointers. Like I said before, shared pointers automatically handle memory management, so I don't have to manually delete entities or keep track of who's still using them whenever I pass them to other classes or interfaces. So as soon as no one reads an entity anymore, it's cleaned up automatically from the vector. There are definitely other ways to implement this, like using raw pointers or unique pointers or an array. I prefer this because it's pretty easy to implement and it makes sharing entities across different parts of the code really easy. And reading the entity list into an std vector is really simple. I'm going to go ahead and do that. Std vector, of std shared pointers, entities types called entities. We're going to have to include a vector here. And just so we don't forget, let's have a getter for it. Vector std shared pointer. We're going to return by reference because we don't want to make a copy of this vector every single time someone needs to access the entities. That's going to make it a bit more efficient. Here we can just return entities. Perfect. Now we're going to have to add a new function to our memory handler to handle reading pointer arrays. For this, I'm going to be using templates because we might be reading other arrays or not entities. It's going to be really easy to implement into other projects or other games. Let's go back to memory handler.h, new template, type name t as well. It's going to return a boolean, read pointer array. It's going to take std uint pointer t address, an std vector of std shared pointers to that type, a reference to a vector, and the size t of the max count of entities we want to read. And we're also going to have a boolean set to check permissions. Check perm because I don't know if I'm spelling that right. It's set to false by default. We need to include vector and we need to include memory. Perfect. Declare that or define it. So whenever we start reading from the list, we want to first clear the list. All list does clear. Now because this is a std vector of shared pointers, if the pointer isn't being referenced by anything else other than the vector, the pointer is automatically going to be deleted, so we don't have to worry about it. If it's being referenced by something else, it's going to be removed from the vector, but it's not going to delete the pointer, and it's going to let the other thing that's referencing it take ownership. So now this makes it really easy to handle the memory of our entities. Now, of course, this is an external, so this doesn't have to do anything with the in-game pointers. This is all on our side. So now we're going to iterate through all the indices and read those pointers into the entities in the vector. I'm going to use the size t here, is less than max count. And here we're going to take a different approach. We're not going to use the number of entities because some games might not have that accessible in an easy way. Especially in L4D2 2, how am I supposed to find the number of entities on this map? That's going to be pain. So instead, we're going to use some heuristic checking to make sure we don't read incorrect pointers. which is why we have this boolean here to check perm to false by default in A++. And that's also why we have max count. So the first thing we're going to do is we're going to get the base address. So std uint pointer t current address is equal to the base address, or the address, which is equal to the address plus I times the size of, I just realized we have an issue here. We're using unsigned int pointers here, which are 8 bytes, and pointers in x86 games or L4D2 are 4 bytes. So it's going to make it really confusing to make calculations for iterating through the vector itself. So what I'm going to do is I'm just going to do Control F, change it, just do std. Actually, I don't have to do that. uint 32t, I think that's what it's called. Entire solution, replace all. There we go. This is basically the smaller version of the uint pointer t, which is going to be 4 bytes instead. It's going to make it match up with our game. Of course, you could keep using unsigned int pointers for that, but it's just going to be a pain for reading entity lists because it's going to corrupt some of your addresses because it has to fit a 4-byte pointer into an 8-byte space. But anyways, let's do the next part, which is calculating that raw pointer. 32t raw pointer is equal to read memory std uint 32t current address, which I misspelled. So right now what this is doing is we're going through the loop where we start right here, which is the base address. Here, I mean, we read the pointer that it's pointing to. So we get this value right here. That's the raw pointer. Now we're going to check if that pointer is equal to 0. If it is, we're going to break out of the for loop because it's invalid. So that would be one of these values. Now we're going to check if the raw pointer is less than 0x some random value. I'm just going to do thousands. So if it's basically one of these values, which isn't really a pointer, but it's not 0. Actually, let's make that a bit bigger. Now we're going to do this part now, which is check permissions. This is going to check that wherever that pointer is pointing to, or that memory region is readable. So if it points to a really big address, instead of crashing when we try to read it, this little check that we're going to do is going to check that that memory region is actually a memory region in the game that we can read. This isn't really necessary most of the time, but when you first start out the cheat, you want to have as little as possible errors as you can, even at the cost of performance. And then at the end, when you're done with the cheat, you can start removing safety checks if you need more performance. So we're going to do a virtual query x. It's going to take the proc handle, the reinterpret cast of LPC void, which is just a weird pointer, to the raw pointer that we have here, the address of MBI, which is that information structure, size of MBI. So this is just getting that information into the structure. And now we're actually going to check that structure for those values. So if not MBI.state and mem commit. So if we can't read from that memory space isn't committed, we're going to break out of it. Or if that MB state of that memory region has data.protects, if it has these flags, that's page read only. Basically, we want to check first if the state is mem commit, if we can read to that region. And it's going to check if it has any of these permissions. If it doesn't have any of these permissions, then we can't read. So we're going to break. Now that we have that, we're going to make a T object, which is basically, in our case, would be the entity. And we're going to read that pointer and copy it into that entity, make it into a shared pointer, add it to the vector list, and then go for the next for loop. A size T for the bytes read. Then we're going to read process memory. So if not read process memory, the proc handle, same real pointer with reinterpret cast, LPC void, the address of the objects, or the address we're reading into, the size of that, number of bytes read. Basically, if we can't successfully read that read process memory function, then that pointer is probably invalid, so we're gonna dip and stop reading any other pointers. Then we're going to do outlist dot in place back std. On another note, if you were using unique pointers instead and you tried using pushback, you would get an error. You can't make copies of unique pointers in a vector, so we have to use in place back for unique pointer. With make shared, we can use either, but in place back just avoids making an unnecessary copy. We don't really care about the order of the entities anyway. And that's pretty much it. And we're just going to return not outlist.empty. If the list isn't empty, we read something, so the function works. Now let's go to the offset handler and finish our read pointers here. Let's go in here and actually finish what we have so far. So we need to read the address of that entity list first to pass it into the read pointer array. So let's call it entities addr is equal to, let's copy this. This is server base, and this is offset entities. And I forgot to declare offset base. Then we're going to call the memory handler read pointer array entities addr, the vector for storing the entities, and the max number of entities. Let's do 64 for now. I don't know if there's more, but it didn't seem like it. And let's check permissions for now. Let's do server base here in the offset handler. Actually, I can just copy this. And I can copy this, paste it, and server instead. Pretty sure that's all we need for now. Actually, we do need to update our entities. So projects, generate C++ code. I don't know if we're going to use this now, but put that in there. We're going to need a vector 3, so let's do struct vector 3. Later on, we're just going to use a library, but for now, x, y, z. I think we just go to main CPP and test it out real quick. For now, I'm just going to print it to the console, but later on, we'll use the overlay. So let me comment all of this out. std vector of std shared pointers of entities. It's going to be a reference because I don't want to make a copy. Offset handler get entities. And we're just going to iterate all of them using auto here. Auto reference to each entity. In entities, we're going to std cout entity.health. Sure. And I think my game is still running. Yeah, it is. Don't run into any issues, which we already did. Outlist. What did I call it? Oh, I just called it back. See, this is following the template functions. You don't really, it's really hard to find errors because they're all runtime errors. This is defined at runtime. The compiler defines all the possible type names at runtime. And now we have a bunch of health for enemies. This is our health. Then we have 50-50. I guess there are a couple tanks. Yeah, I did spawn a couple more just to make sure. And it seems to be working. Last one is 50. And if we go back to the entity list here, let's do a pointer and let's check the health. EC is 50. So this is correct. It does stop correctly right here, which is perfect. So that's going to be it for this video because I think that's already a pretty long one. So for next video, I'll probably start trying to find the view matrix so we can start using the ESP and also integrating all of these classes together so we can start using this menu that we have here a bit more. Because right now it's just a tiny little button. Anyways, enjoy the holidays. Thanks for watching and peace.